So it's joint work with Zvika Berkersky, who's a cryptographer at the Weizmann Institute in Israel, Paul Cristiano, formerly from UC Berkeley, now at OpenAI, Urmila Mahadev, who's a postdoc at UC Berkeley, and Umesh Vazirani from UC Berkeley. You can hear me, right? Because it's been okay, excellent. Okay, sorry about that. I'm happy to talk about this. It's work that I like, and one of the reasons that I like is that I think of it as building a bridge between two different areas. It's a bridge that's built out of ideas from cryptography, and it goes from the area of what's sometimes called self-testing or Bell inequality violations or non-local games. So it goes from brings or allows us to bring a lot of results that were developed in that area based on the assumptions of spatial isolation into a setting where we cannot make this assumption anymore, where we don't have the ability to do Bell tests, but instead we're willing to place computational assumptions on the quantum device with which we're interacting. So the goal of the talk is to try to explain what this bridge is and what it's built of. What I wanted to try, I wanted to start a little bit broad, just by recognizing something which is hard for some of you here, including me, who weren't there when quantum computing started, because it started really fast in a very impressive way. It just in a few years, there were these results that said basically that, look, I mean, there was this machine that you could build using the laws of quantum mechanics, and you could make it in principle in a fault-tolerant way, and it could solve problems such as factoring that we had no idea how to solve on classical computers. So I think this was very impressive, but it was also very theoretical. This is what the best approximation to a quantum computer that you had at the time. So now time has passed, 20 years have gone on. And I think we were all aware that there's some kind of a phase transition going on in quantum computing. And so what happened is that we still don't have a quantum computer, but we're starting to get something that's even more interesting in some respects. So we entered this era that my colleague John Preskill calls the NISQ era, where we have small or medium-sized devices that are not able to implement fault tolerance, yet bring us close to what you can refer to as a experimental test or violation of the extended Church-Turing thesis, that postulates that any process that can be efficiently or naturally implemented can be efficiently simulated on a computer. And these quantum devices are there, and they're doing things that we don't seem to be able to simulate on classical computers. And I think that's very exciting. It's very exciting to try to figure out what the extent to which this is happening, right? So when is it that we can say that there's been a violation of the extended or computational, it has lots of names, Church-Turing thesis. So there's a lot of work on this question, of course, and it's not quite the topic of the talk, so I don't want to say too much about it, but I think it helps set the stage. So this is, of course, there's the famous work by Aronson and Arkhipov on boson sampling. There's the work by Bremner and co-authors on IQP circuits, and then there's the proposals from Google on sampling from random circuits. So I think a lot of you are familiar with these. I'm not going to review them in detail. The reason I'm putting them up is because I want to point to a few features that they have, or rather from the perspective of this talk, deficiencies that we're going to try to overcome. So one of them is that these tasks are all fairly artificial tasks, right? I mean, generally the goal is just to create a quantum circuit that's selected from a certain family of random circuits and then implement the circuit and sample from the output distribution. And so there's not really any particular reason why you care about that circuit, other than it allows you to maybe demonstrate something that you couldn't do classically. And these are tasks that are designed for circuits that have around 50 or 60 qubits, and there's a good reason for that. You want to use at least 50 or something qubits, because anything below you can simulate classically, so it's not going to be interesting. But also, you couldn't go much above, right? So if you implement boson sampling on the 80 qubit or 90 qubit quantum computer, then you don't know, right, what happened. The problem is that these tasks are almost as hard to verify as they are to simulate on a classical computer. And so they target a very narrow regime of sizes of machines. And finally, one last sort of limitation of them is that it's hard to see where you're going to go after you've made the demonstration of quantum advantage based on one of these tasks, right? So if you implement a circuit and let's say you manage to verify that it's sampled from the boson sampling, it implements a boson sampling experiment. So you can publish a paper, right, in Nature. But then what, right? What do you do next? Next, you're going to make your machine bigger, right? It'll have 80 qubits, and then what, right? So you didn't learn anything about the machine aside that from the fact that it did something that you couldn't do classically. And so you have this kind of interesting picture where when we create these machines, then we're building some theory and some potential tests that might be practical, that say something about these machines. But then there's bigger machines, right? And there's a whole range before we eventually get to a situation where we don't worry about these questions anymore because we have a fault-tolerant quantum computer. It's maybe able to break elliptic curve cryptography or RSA, and then we won't really worry about demonstrating that it's there's a quantum advantage or not because it's doing something that we really care about. But then there's this whole regime there. And what's going to happen there, right? So here we're going to do simulations, maybe quantum chemistry, physics, and the simulations are going to produce some results, and then maybe we can do experiments to validate these results. But when is the theory going to kick in? When will we have confidence that the machine really is implementing the task that we asked it to implement? So I think that's a question that's interesting, and it's a question that I'm not going to solve in the talk, but it's sort of we're making steps in the direction of thinking about it. Okay, so at the other end of the spectrum, and this is going to be our starting point, is the setting of Bell inequalities or Bell tests. And so that's a setting that's been much explored from a theoretical point of view, where we have sort of much stronger results theoretically. So there's been experiments. So this is the experiments by Aspect starting in the 80s, and more recently, this is one of the first loophole-free Bell inequality violations that took place in Delft a couple years ago. And so it's known since the 80s and a little bit later for the more numerically robust results that if you manage to set up an experiment that allows you to witness a sufficiently high violation of an appropriate Bell inequality, such as the CHSH inequality, then you can obtain very strong guarantees on the quantum system that was used in order to violate that inequality. Not only that it was a classical system, but also that there must have been something that's pretty close to an EPR pair that must have been measured in certain bases. So not only this, but recent work in theory in recent years has scaled up this observation. And by now we have very efficient, from the point of view of verification, statistical tests that can be implemented with two quantum computers that are at isolated locations, such that if the test passes, which is easy to verify, then we'd have confidence that these devices or computers share not one EPR pair, but n EPR pairs for any n, and the test is going to scale very efficiently with n. So you can think of those as efficiently verifiable tests of quantumness, where now the verification machine interacts with two quantum computers that share a lot of entanglement. And we can not only test that these systems have very high dimension, right, because any EPR pairs need a very high dimension, but we can build a lot on top of that. So we know how to do various cryptographic tasks, such as randomness certification, also quantum key distribution. We know delegation protocols that can be built out of that. So there's a very strong theory in that direction, but the problem somehow is that implementing these Bell tests remains challenging. It's necessarily more challenging than the kind of setups that I had on the previous slide, because you need not only one computer, you need two computers. But more important than that, these computers need to share a lot of EPR pairs simultaneously. These EPR pairs need to have very high fidelity. And if you're really interested in asking the foundational question, which is, does my computer really have this exponential state space that it pretends to have? Does it really have n EPR pairs? Then you'd want to implement these Bell tests in a loophole-free manner, which, if you want to do it with thousands of, or let's say even hundreds of qubits, is very challenging. So in a way here, the theory is very strong in the kind of results that we can derive. But from an experimental point of view, it's less satisfying than if we could achieve similar things with a single device. So this is what we want to try to do. So that's the setup for this talk, I'm going to design or present protocols in which a just classical verification machine interacts with a single quantum device in order to demonstrate similar things that were presented in the previous slide. So we're going to have to replace the spatial isolation assumption by another assumption, and that assumption is going to be that the quantum device may be powerful. So I might need a fault-tolerant quantum computer in order to implement this, but I'm going to make a stronger assumption, which is that it's not more powerful than a full-blown quantum fault-tolerant computer. Okay, so it could be a fault-tolerant computer, but it's not going to be more powerful than that. And specifically, I'm going to assume that this machine cannot solve a task that comes from cryptography that we don't think that any quantum computer should be able to solve, but it's going to be an assumption that we have to throw in. So even then, I have a quantum device that's in principle more powerful than my classical verifier, right? I mean, at least it has a quantum computer, even if that computer is not more powerful. So it could be sufficient as a setup, but it turns out that for our results, I'm going to need a little bit more leverage. And this leverage is going to come from the fact that the cryptography that I use is going to be based is going to use a scheme that has a trapdoor. A trapdoor is some secret information that the verifier is going to be able to hold on to that allows it to achieve a certain task, a certain inversion procedure, more efficiently than even the quantum prover could do. So this is how we're introducing asymmetry between the verifier and the quantum prover. A priori, this machine is more powerful, but now the verifier is going to gain leverage by setting up the cryptographic scheme in secret and holding secretly the trapdoor information, and that's going to allow it to test that the quantum device performs a certain task. And so our goals are, the first main goal is that I want something that scales in terms of the efficiency of the verification. So this should be something that I can implement at small sizes of qubits, but also at larger sizes of qubits. Not only that, but I'd like to have a little bit more. So I'd like to be able to go inside the device and get a characterization of what it is doing. Not only that it's doing something that's quantum, not classical, but I'd like to know how it's doing it. I'd like to have a theorem that says, well, I mean, this device has a qubit in that region, and it's been measuring it in different ways, and this is the reason that it succeeded in my protocol. Because if I have that, then I can build more things on top of it. And so finally, we'd like to be able to use this protocol in order to have a task that's useful. And in this particular talk, the task is going to be a certifiable randomness generation, which is sort of a first step towards other cryptographic protocols. So let me give you the idea for how the protocol is going to look like. And some of you are already familiar with this, because at this point, I'm going to go over things that Urmila Mahadev covered in her talk yesterday morning already. But I'm not going to assume that everyone was there, so I'll go over it again. So the setup is like this. So we have our verifier and we have our quantum device, and it's going to be a 4-round protocol. So at the first step, the verifier sets up the crypto. So it selects some public and private parameters for the cryptographic scheme. I'll explain that on the next slide. It keeps the private parameters to itself and sends the public parameters to the device. Okay. So then the device is supposed to accomplish a certain quantum task, and it does it. Maybe. And then it returns to me a classical string that I'll refer to as the commitment string. Okay, so the verifier receives that commitment string. And then the second phase is going to take place. This phase is called the challenge phase. So the verifier is going to flip a public coin that specifies the challenge that the device is supposed to answer. So there's 2 challenges labeled 0 or 1. And then the device is going to answer these challenges, and the verifier will check the answers. So that's the structure of the protocol. Now let me tell you what's special about it that's going to be able to at least make this protocol into a test that the device does something that's quantum, that's not classical. And the main idea is the following. What we're going to do is instantiate this scheme with a cryptographic construction that is such that we can prove under computational assumptions that it's impossible for any device, classical or quantum, as long as it's bounded polynomial time, to answer both challenges simultaneously. Okay, so it would just be impossible computationally to find a valid answer to 0 and a valid answer to 1 at the same time. So I claim that if we've managed to instantiate a cryptographic scheme that has this property, then we're done already. The reason we're done is that if a classical device was able to succeed in my protocol with probability just even a little bit larger than a half, then it must have in mind, or it must have the ability to answer both the 0 challenge and the 1 challenge. And because it's a classical device, I can run it on the 0 challenge rewind it, trace back the memory, and then run it on the one challenge, get both answers, and then it violates my assumption. Whereas for a quantum device, this is not necessarily the case. It could be that I have a quantum device that succeeds in the protocol, but the way it succeeds in it is by making a certain measurement, and that measurement might be a destructive measurement that enables it to obtain an answer to the challenge that it was asked about. But once it's made that measurement, the state has changed, it's collapsed, and that prevents me from saying, well, okay, but in fact, I could go back in time and also extract from that device an answer to the one challenge. So this is what we're going to do. In a way, this is a protocol that checks that a certain device implements a collapsing measurement, something that cannot be rewound as a classical device would, as you could do with a classical device. So let me say a little bit how this is done. So it's based on similar cryptographic primitive that was introduced in yesterday's talk. So it's a primitive called trapdoor claw-free functions. So what's a claw-free function? First, it's a pair of functions. Both of them have the same domain and range, and they're bijections. So they look something like this. So because of the fact that both of them are bijections, any point in the domain, in the range of the functions, has exactly one preimage by the one function and exactly one preimage by the other function. And so this is what we call a claw, like two preimages that get mapped to the same image by the one function and the other function. And the cryptographic assumption on this family of functions is going to be that in general it should be computationally difficult to find a claw. So it's always, it should be possible to evaluate the functions. So given a point in the domain and the choice of a function, I can evaluate it. But it should be computationally difficult to find 2 points that by the one function and the other map to the same value in the range. And then the last assumption is that we're going to construct a pair of such functions that on top of this has a trapdoor. Trapdoor is just like some classical information that allows you to invert the function if you're given this extra classical information. So let's suppose that we managed to construct this pair of functions, and then let's see something interesting that we can do with them using a quantum computer. So the most natural thing to do with a quantum computer is to evaluate the function in superposition. So what I'm going to do is create a uniform superposition over all bit strings of n plus 1 bits, and then controlled on the first bit, that's going to be 0 or 1 with probability half, I'll evaluate the f0 function or the f1 function on the remainder of the superposition in an ancilla register. And then when I measure that register, that corresponds to measuring a uniformly random point in the domain there, in a way that the preimage register is going to collapse to a uniform superposition over the exactly 2 preimages that that point has. Right, so this is very straightforward. Create a uniform superposition, evaluate the 2 functions on the superposition by controlling on the first bit, measure the image, and the preimage collapses to that superposition here. Okay, and at this point I can do one of 2 things. The first thing I can do is I could measure this register in the computational basis, and this would give me 1 preimage at random. This is something that I could have done also classically by doing things in a reverse order. Select a random preimage and then apply one of the 2 functions at random. In this way I would have obtained a y and I would have obtained x0 or x1. But of course there's something else that the quantum computer can do. It's not limited to measuring in the computational basis, it can also measure in the Hadamard basis. And I'm not going to go over the calculation again, but if you measure this state in the Hadamard basis, this is the same thing that happens in Simon's algorithm, for those of you who are familiar with it. What's going to happen is that you're going to obtain a bit string D that is such that the inner product mod 2 of D with the parity of these 2 strings is equal to 0. And here is where you've done something interesting. This is not quite the same as recovering both preimages, but it's 1 bit of information that is information jointly about the 2 preimages. So in order to make use of this, we're going to strengthen the assumption that claws are hard to find into this thing that's called a hardcore bit property. So my cryptographic assumption is going to be that the functions are set up in a way that it's computationally difficult, given the description of the functions, to simultaneously come up with a preimage, 1 of 2, x0 or x0, and a non-zero equation in the parity of these 2 preimages. Okay, and note that the fact that this is computationally difficult is not a contradiction with what's written on that part of the slide, because the quantum device is not able to implement this and there, right? I can either measure in the computational basis or in the Hadamard basis, but I cannot do both simultaneously. I was going to give you an idea of how you construct these functions based on the learning of errors problem. Just to give you a sense that it's actually not difficult. I mean, proving the properties is hard, but the construction of the functions is very simple. You could think of them as just like matrix vector multiplication. That's essentially what these functions are doing. In particular, they're not necessarily that hard to implement as a circuit. I'm going to skip the description in the interest of time. And move on to the second part of, I have a little bit more. Move on to the second part of the talk, where I want to go beyond this, that was a test for quantum behavior, right, a test for collapsing measurement, and explain how to leverage that and go a little bit deeper inside the device and extract something useful for it, which is certified randomness. That is going to be information theoretically secure randomness based on the computational assumptions. So I want to explain exactly what I mean by that. So we're all familiar with the fact that quantum devices can generate randomness. You just initiate a qubit in the plus state and measure it in the computational basis. There's things that these kind of computers, they exist, and you can buy them. This is one from Vidick Quantique. But then the question is, if you do this experiment and you only observe the input-output behavior of the device, then what confidence do you have in the fact that the outcome is actually random, right? So can you do a test for this randomness? So it's sort of the cartoon there where you see the output of the device and it's just a string of bits. And how do you know if these bits are random or not? Because randomness is not a property of any particular string. It's a property of the process that generates the string, right? So what we want to say is that this process is a randomness generating process. So there's been a lot of work in the setting of Bell inequalities where you can assume spatial isolation that leverages the observation of Bell inequality violation in order to certify the presence of randomness. And the way these things proceed in general is in two stages. At the first stage, you apply things that are known as rigidity theorems that basically demonstrate that if you have a large enough Bell inequality violation, then the device must be measuring a qubit in certain bases, and so that generates randomness. And then there's a more difficult part that leverages that and repeats it multiple times in order to get not just one bit of randomness, but multiple bits of randomness. So now what I want to do is sort of import this, as I described at the start, into the setting where I don't have Bell inequality violations, but I have a single device. And so let me explain how we're going to do this based on the same ideas that went into the protocol that I described earlier. So I'm going to flash the protocol back on the slide just to remind you. So in this protocol, first the verifier sets up some crypto, sends public parameters to the device, who replies with a commitment, and then there's this challenge, 0 or 1, which was like measuring the computational in a Hadamard basis. The device replies either with a preimage or with an equation, and the verifier checks that. Okay, so how do we use this in order to generate randomness? Let me tell you where we're going to get the randomness from. We're going to get it from the answers to the 0 challenges. So here the device should reply an x0 or an x1 preimage, and the randomness will just be which one did it return to me. So the things are going to be set up so it's easy for the verifier to tell if the preimage is a x0 kind of preimage or an x1 kind of preimage, and that's going to be the one bit of randomness that we get. Right? I need to argue why this is randomness. The first thing to argue is that I want to change the protocol a little bit so that I can get more randomness out of the protocol that I inject in it. So there's a lot of random choices that are made by the verifier in this protocol. It has to set up the crypto, and it has to select these challenges randomly according to just an unbiased coin flip. So in order to save on the randomness, I'm going to bias this. Because the randomness will come from the C equals 0 rounds, I'm going to play these kinds, initiate these kinds of challenges much more frequently than the others. So this is something that's very standard in this area of randomness certification. We bias the distribution on challenges. So I'll do that. And the other thing is that we need to save a little bit on the randomness that's used to instantiate the cryptography. And so I'm not getting into that, but we'll select all these public and private parameters in a pseudo-random way so that they don't use so much randomness, and we can amortize the randomness that's needed in order to do that over the multiple rounds of the protocol. Okay, and I already mentioned that. So that's the protocol. And now I want to just give you one slide idea as to how do we argue that this protocol generates randomness. So the idea is going to be to think of this device in a slightly more high-level way, coarse-grained way, by thinking of just one bit of information that it returns on each of these challenges. So on the 0 challenge, the bit is going to be, is it an x0 or an x1 preimage? That's just one bit. And on the one challenges, it's just going to be, the bit is going to be, is this equation satisfied or not? So in this way, at a slightly more coarse-grained level, I can model my device using only two observables. The observable that it measures on challenge equals 0 and returns this bit, which preimage it is, and the observable that it measures on challenge 1, and that says whether the equation is correct or not. Ah, okay. Thank you. Okay, so I model it at this higher level, and this is what I'm writing here. And so the property, this hardcore property, the way the crypto is determined, the way the crypto is set up, you can argue that these two measurements need to make an angle with respect to each other. So if these two measurements were aligned, commuting, or even almost commuting, then you could run the one forward and then the other forward, and you could apply techniques such as the gentle measurement lemma in order to argue that these two measurements can be measured approximately simultaneously. But if they could, then you'd have a device that violates the this hardcore bit property that I mentioned earlier. Right? So the fact that it's hard to find both a preimage and an equation says that these two measurements must be very incompatible. In particular, they must make an angle with respect to each other. Now, two observables that make an angle with respect to each other basically look like sigma x and sigma z. There's nothing else up to a change of basis, as long as the angle is, right enough, as long as you have the right angle. So this is what we do in the proof. We look inside and we say, look, I mean, these two observables, there's no choice. They must make this angle. In the correct basis, they look like sigma x and sigma z. And once we have that, then we're almost done. Then we can look back at the protocol and say that because you succeed in this protocol, I mean, otherwise I'll just reject, in this kind of challenge, you always give me a valid equation, which means that whatever state you're measuring at that step must be a +1 eigenstate of the associated observable, which is that observable here. But if you're a +1 eigenstate of that observable, when I measure you in, so that would be a plus state, when I measure you in that basis, I'm going to get a random bit. So now I've managed to get into the device and say, like, look, I mean, this is what it's doing. Really, it's measuring a qubit, and measuring a qubit gives me some randomness. So that's the main idea in the analysis, and maybe just to flash the parameters once you de-randomize the whole thing properly. So we end up with a protocol in which we repeat this as many times as we want, n rounds. These n rounds in total consume only a polylogarithmic amount of randomness, but we can argue that they generate a linear number of bits of entropy. And here I just want to emphasize this, which is that I made a computational assumption, right? The assumption is that this device is not able to break the cryptographic scheme. If it does, then it can succeed in my protocol deterministically. But if it doesn't break the cryptographic scheme for the duration of the protocol, and I record the bits that were generated, then these bits are information theoretically random. There's no computational assumption anymore. Someone can break the cryptographic assumption later. That's fine. It's not going to be able to allow them to get any information about the bits that the verifier recorded during the protocol. So let me summarize and give a few questions. So just to summarize, so I described this protocol by which a classical verifier can interact with a quantum device, and it has the basic protocol is a 4-round interaction, and then in order to get more randomness out of it, you repeat that basic building block n times in a de-randomized fashion. And then we have the property that if the device succeeds in the test that's performed in that protocol, and if it doesn't break the post-quantum cryptographic assumption for the duration of the protocol, then the outputs that are recorded by the verifier are statistically indistinguishable from uniformly random bits, let's say after you've applied the randomness extraction procedure. I didn't really describe the implementation, so I'm going to skip that comment. And I just wanted to mention, but I think it's clear that some of the ideas in this talk have been used by Urmila Mahalev to, she presented them to achieve delegated computation yesterday, and right after she's going to talk about also building on these ideas in order to achieve homomorphic encryption. So in the last minute, I want to go over some questions because I think that's one of the main things about this work is that this bridge that it's building, and then what do we do with that bridge? I think there's a lot of things that we could do. One thing is trying to move towards implementation. So I started motivating my talk by these questions about near-term devices. This is not near-term implementable because for all I know, it needs a fault-tolerant computer. But I think it is possible to move in that direction. This learning with errors cryptographic assumption is used in classical cryptography, and it has been optimized almost to death. And there's variants of it called ringed learning with errors that can be implemented using low-depth circuits, using fast Fourier transform. So if you could do that in our case, you'd get a protocol that can be implemented using a low-depth circuit. I don't know how to do it because the Ring LWE has a little bit fewer theoretical properties than the generic LWE, but that's sort of work in progress. Another question is whether we could just get rid of that assumption and implement the protocol on more generic assumptions, such as quantum secured one-way functions. And then here are some other questions that I leave on the board, but I'll stop because I'm out of time.
Okay, thank you, Thomas. Questions?
When you argued that the observables were essentially sigma x, sigma z, are you making an assumption that your device is a qubit there?
No. So in general, these observables, when I start my security proof, the observables are arbitrary observables acting on an arbitrary Hilbert space. And the only information that I have about these observables is that they're very highly incompatible. Otherwise, I would have a contradiction with the cryptographic assumption. Then you can put your hands into it and say, well, if that is the case, then there is a change of basis, such that in this new basis, they must look like sigma x and sigma z. Okay. So I'm not saying the device actually works in the basis that I have in mind, but I'm saying that from a mathematical representation of what the device does, it's equivalent to measuring a qubit in those bases.
Okay, thanks.
Thanks.
Does your protocol make an IID assumption?
Nope.
No?
So I skipped over that, but the way we eventually obtain strong statements on like linear entropy and things like this is by importing results that have been developed for the same task in the non-IID setting for when you have Bell inequality violations. So we use a little bit from two different frameworks. One is by Miller and Shi, and the other is by Arnon Friedman, Dupuy, Fauzi, Renner, and myself. It's this entropy accumulation. So we use these tools in order to deal with the non-IID setting.
All right, thanks.
More questions?
Hey, so is there a sense in which you use this to kind of define a computational analog of the Bell inequality? Like, is that a meaningful thing to talk about?
I'd like to be able to say that, but I think we're not exactly quite there yet. So I think there's a little bit more sort of exploratory theoretical work to be done before I can make that statement. Right now, we only had this one qubit, and we had a pretty good characterization of that one qubit. To say that we have a computational Bell test, I guess we're working on it. So I think this is like a natural next step, and then continue building on top of that. But this is sort of initial stuff. Thanks.
Okay. More questions or something? Okay, I'll ask maybe another question. Thomas?
Yeah.
You just need to.
Yeah, it's okay. You can.
Yeah.
What?
Am I good? No.
One more? Okay, sorry. Yeah.
Oh, sorry. You've called this a cryptographic test of quantumness, but it seems like there are some quantum things that a prover wouldn't have to be able to do, like, for example, implement a universal gate set in order to pass your test. So, like, can you talk about what exactly we've proven what quantumness means?
Oh yes, I mean that's a good question. So it's really quantumness in a I would agree in a fairly weak sense, in the sense that maybe it would be more fair to call it a test of non-classicality. I mean, specifically, you saw how far I went, right? I went as far as to say that assuming quantum mechanics is a correct theory, so I can model like any device that's in my protocol using quantum mechanics, then that particular device must have a qubit that it can measure in two mutually incompatible bases, which is something like a classic, classical mechanics wouldn't allow me to do that. But I've definitely not tested like a full-blown computation for sure. I mean, yeah, thanks.
Okay, so last question. Did you consider a scenario where you have a quantum adversary outside of the computer? Correlated with it, and then you want
yes. So I didn't put the technical statements on the board, but if I interpret the question correctly, the question is, well, is this randomness that you certify, like it's this randomness to whom question, right? How strong are your guarantees? And so guarantees are that the conditional min entropy of the randomness that's generated, conditioned on any quantum state that might be correlated with the device initially. So it's allowed that there be an adversary that sets up the initial state of the device that's executing the protocol and then keeps some correlated quantum information, but then just sits on the side, only sees the transcript of the protocol, and at the end, that device that had correlated quantum information also cannot predict the output bits.
Okay.
The device, on the other hand, can, of course. So, yeah.
Okay. Thank you. Let's thank
Thanks.